Okay, so we're getting to our final wrapping it up in our unit here on redox reactions. This is the section where we bring it all together. This is kind of the most technical stuff that you have to do, which is balancing chemical reactions. Sorry, I got it on the wrong slide. Balancing redox reactions using something called the half reaction method. At first, I know this is going to seem like maybe why do we need to do this, but I broke this section into two shorter videos. One kind of focusing on the simpler parts of it, just sort of the setup, and then the second video goes into a little bit more of the challenging type ones that you're going to come along with. So I know it's going to feel a little awkward, like, why is this going on? But really, I promise this is once you get the idea, the hang of this procedure, it'll make sense to you a little bit better. So why do we have to do this, first of all? Why can't we just balance them like we've balanced them all year long? Well, you know, we already know this, that in every chemical reaction that you have to balance the total number of atoms, the numbers and types. So you can't have, 3 carbons on the left and then a different number of carbons on the right, or oxygen appearing out of nowhere, that kind of stuff. And we know that. But what's happening in redox reactions, because electrons are being transferred, we have to balance the equation for electrons as well. Furthermore, because we're talking about things changing charges, we have to also balance the overall charge of the reaction. I know the reactions are supposed to be balanced from the beginning and the end, but it's because a lot of times these reactions are presented to us in their ionic form, where it looks like there's a charge on the left and there's a charge on the right. We have to make sure that that balances out, because in real chemistry, that charge would be balanced. So again, that's why we have to do this different balancing method. And the equations I'm going to use in this particular section, 18.3a here, it's not going to be as hard. You can balance these pretty straightforwardly. It's in the second half when we get into the more realistic ones that you'll see why we have to kind of go through this whole rigmarole process. So, in terms of doing this, first of all, to go through the process, you've got to identify what's being oxidized and what's being reduced. These are called half reactions. We know that there's an overall reaction, but we want to say, okay, this is the half reaction that's oxidation, and this is the half reaction that's reduction. So you'll be given an equation like this one, and this is cerium 4 plus and tin 2 plus is going to eventually produce cerium 3 plus and tin 4 plus. So again, a lot of times these are presented in their ionic form. It's like, where's the rest of it? It's there. It's just they're spectators, so we don't need to make them show up in the reaction. So step number 1. Write them out as oxidation numbers. You have to assign your oxidation states. You got to know what they are. In this case, they're given to us because ionic charges are oxidation numbers, so that's kind of nice. And then you can write it out as 2 half reactions. It does not matter which one you put on the top and which one on the bottom, so pick an element, it doesn't matter. In this case, I noted which one was oxidation, which one was reduction. Again, the one that's with the charge that reduces is the reduction example. But again, write them out. Here's half reaction number 1, here's half reaction number 2. Okay, moving on. The next thing that you have to do is you have to be able to figure out how many electrons are actually changing hands in each half reaction. So if we take a look at this tin example, the first half reaction, there must have been 2 electrons that shifted hands because the charge changed by 2. Now you can only add electrons, so you have to put them on the more positive side, because 4 plus and 2 minus is going to give us a charge of 2 plus. If I put the electrons on the other side, if I made a mistake and put them on the left, then I'd have 2 negative and 2 plus, and that does not equal 4 plus. So the charges have got to add up across to be consistent left side, right side. Not add up to 0, but add up to each other. So in the bottom one, you can see in the cerium equation, the charge is only changed by 1 from a 4 plus to a 3 plus. So I add that electron on the more positive side, and it's just 1 electron. So if you've done it right, in one of your half reactions, there will be electrons on the right, and in the other one, electrons will be on the left. And again, it doesn't matter which one's top and bottom, but that's how you know you've done it right. If you have 2 half reactions with electrons both on the same side, you did something wrong. Go back and double check what you did. Okay, next part, we have to balance the number of electrons. This is that idea that electrons gained has to equal electrons lost. We have to make sure that the reactions that we have on paper accurately represent what's really happening, and we wouldn't have extra electrons sort of wandering about lost. There must have been an actual number on there. In chemistry, when we're balancing equations, we use coefficients. Same kind of idea here. But the tricky part, makes it a little different, is now we can't just use a coefficient in front of an item. We have to use a coefficient in front of the whole equation. And you can see in the second equation down here, I put parentheses around that whole cerium equation and put the 2 out in front. Why did I do that? Because 2 electrons were shifted gears in that first reaction, so 2 electrons must have shifted in the second one. Top 1, 2 are lost, so the bottom one means 2 had to be gained. So that's where this 2 came from out in front. So like I said, you're going to use coefficients around an entire equation, and you're going to distribute it in the next step. It is possible, in some cases we'll see in the next video, that you may have to put coefficients on both equations, where you have like a 3 on the top one and a 2 on the bottom one. That happens pretty regularly. Okay, moving on. Next step. So now you're going to distribute and add the two reactions together. The whole goal here is that we should eventually end up with the number of electrons gained equals the number of electrons lost. They should be able to cancel out by the time we add these equations together. Why are we adding them? Because remember, they're actually happening in the same container. So we just want to take a look at overall what's going on. So you can see what I've done. I've distributed my 2 across the whole equation here. So I have 2 electrons, 2 cerium 4+, and 2 cerium 3+. And then just like you do in algebra class where you're adding a system of equations, I add the things together on the left side of the equal sign, and then I add together the things on the right side of the equal sign. Well, chemistry, we don't have an equal sign, we have arrows, but it means essentially the same thing. So here's all 3 of my things that are on the left side of my arrows, and then here's all 3 of my things on the right side, my products, and they all appear now in this single row down at the bottom. So again, you should have the same number of things in that bottom equation that you had at the top. These do get kind of long, so you kind of need to leave yourself some space. So everything on the left, everything on the right. Now what? Well, just like when you're doing algebra, you combine like terms. And then cancel out stuff that's the same on the both sides. So in this case, your electrons, we had 2 electrons on the left and 2 electrons on the right. By the time I move those over, they cancel each other out. 2 electrons gained, 2 electrons lost. So we can basically cancel them out or erase them. And then we've got our coefficients out in the front here. So this is 2 cerium 4+, and then 1 tin 2+, and 2 cerium 3+, and 1 tin 4+. Now, is this actually balanced all the way across? Well, it has to be balanced in terms of electrons, has to be balanced in terms of atoms, and it has to be balanced in terms of total charge. Electrons are already balanced because we set it up that way so they would cancel out. So they're already gone. Checking atoms, are they the same? Yeah, 2 to 2 for cerium and 1 to 1 for tin. So it's balanced by atoms. Is it balanced for total charge? Well, you take a look at it. We have 2 times 4+ is 8+, and then 2+ over here gives us a total of 10+ charge on the left side. And then this is not oxidation numbers, this is actual charge. And then on the right side, we've got 2 times 3+, which is 6+, and 4+, which is a total of 10+ charge on the right side. So yeah, we're balanced now, all 3 ways. Balanced by numbers of atoms, balanced by electrons. We in fact engineered it that way so they're canceled out. And now we're balanced in terms of total charge. So here's the ideas in terms of what we're doing. I know this is a short one, this is a pretty straightforward, but this is the idea that we're trying to get. We need to have it balanced 3 ways: atoms, electrons, and charge. How do you do this? Number 1, you identify your 2 half reactions. Here's a redox, here's an oxidation reaction, here's a reduction half reaction. Next thing, you're going to add your electrons to make sure that, well, okay, charge changed by 2, so there's 2 extra electrons here. Then you're going to use coefficients to make sure that your electrons cancel out. That's how we balance it, by electrons. Add those 2 reactions together so that all of your left side species are together, all of your right side species are together. And then make sure that you're, at the end, canceled out anything that's identical, and then make sure that your overall atoms, overall charge are there. Keep in mind, I'm going to go back a slide here. Keep in mind, notice how I didn't get lazy. And this is important for you guys. You have to write the charge every single time. You'll see in the next video that it gets really important. We can't cancel these 2 out because they're not exactly identical. And that's a question that comes up. Why, if the 2 electrons are the same, why aren't these 2 ceriums the same or the 2 tins the same? Because they have different oxidation numbers. They're not exactly the same species, so we can't cancel those out. In fact, that's what we're looking for. So there you go. Those are your big ideas. Take a second to kind of process that one, go back and look at it again, and then watch the second half of this. Second half gets more complex, so you got to make sure you kind of got your brain wrapped around this part first. See you in a couple minutes.